Hi class. So today I will talk about section 2.3 Math 130 Calculus 1. We're going to talk about calculating the limits using limit laws. Okay. So we need some rules for computing limits. Charts, graphs, tables, don't always work. We will use the following properties of limits called limit law. Okay, so let me label it over here to calculate the limits. So what is limit laws? Suppose C is a constant and following limits exist. Limits fx limit of x when x approach to a equal to L, and limits of g of x when x approach to a equal to m. Okay, so we're gonna have first one, limits of fx plus or minus gx when x go to a is going to be equal to L plus or minus m. Okay, so this is called like the limit of a sum difference. Is a sum difference of the limits. Number two, you have limits limit of c of fx when x go to a, we're going to equal to c times L. So it means the limit of a constant times a function is a constant time the limit. And number three, if you have like multiplication or the product between fx and gx over here, I think the limit of that when x go to a, so that's going to be the value of limit fx multiply the value of limit of gx, which is L to m. And then the limits of fx when over g of x for when x approach to a is will be equal to L divided by m if m not equal to 0. Okay, so this is a limit of quotient. And then limit of fx everything go everything to power n when x approach to a. We actually, you can take the parenthesis outside of the limit, and then you're gonna have the power n for everything, and then it's actually equal to n. To L to power n, with n is a positive integer. Okay, and number 6. You have limits fx to power 1 over n when x go to a is going to equal to limit of fx when x go to a everything power 1 n which equal to root n of L. So let's using these all limit laws and do the example 9 over here, right? So we're given limit of fx equal to 4 when x equal to a, and limit of g of x when x equal to a equal to 5, negative 5, I mean, and then limit of 8x when x equal to 2 when equal to 0. So apply the limit law. This one I'm gonna apply the first one over here, right? You're gonna have 4 plus 4 plus 5. You also have to multiply. You have to. This is also, this one also come from number 2. So you can multiply 5 by the negative 5. Okay. So Yep, let me clean this up. And how about this? I'm gonna slow down and write like this so you guys can understand clearly. Let's say limit fx when x go to 2 first, adding with 5 limit of g of x. I should move out the number 5 here outside the limit when x go to 2. And then you're going to have equal to 4 for the first limit plus with 5 times with the -5 for the second limit. And that's going to give you what? 4 minus 25, which is equal to -21. Okay. That should be the answer. Let me move up. So, problem B, limits of gx to power 3, right? So I would like to apply number 5 over here, right? I'm going to have parenthesis limits of g of x when x go to 2, close parenthesis, and to power 3. So I want to take power 3 for this limit, and then the limit of g of x equal to -5 from the given, and then it's power 3, and that is your calculator. You're going to have -125. Let's move up. Okay, so C, I have a quotient. Oops, I have a quotient. So this problem I will need to use. Let me use isocolor. I will use law number 4, right? So I have limits of g of x when x go to 2 divided by, let me go up here, limits of fx when x go to 2, and that's going to be equal to g of x, limits of x going to be equal to -5 divided by x going to be 4. Okay, so that will give me -5 or 4 as the answer. Note that the f of x in here is not equal to 0, right? Because it's equal to 4. So that doesn't make this undefined. Okay. Okay. So let's see. Okay, now so let's move to problem D here. I have limit of 1 over hx when x go to 2. For this problem, let me write it as, let me see. Okay, so remember that this one is not equal to the 1 over limits of x. It's not equal to that. Okay, so you guys should not mess up with that. You guys should have So think like this. Let me separate this. You know that the limit of 1 over 8x when x go to 2 can be rewrite as limits of 1 over 0 when x go to 2, because 8x in here equals 0 when x goes to 2. So in this case, you can write ways, make it equals to infinity. Okay. Because for anything that's positive in the top, in the bottom is 0, then it's become undefined. But yeah, we write it as a infinity is the answer. So, or do not exist. Okay. Okay. All right. So let's go to problem E. I have limits of square root of mx when x go to 2, right? Let's see which one I can apply. I would say we can apply, let me use other color. We can apply number 6 over here for part E, because remember that the root here is actually mean, the square root here actually mean power 1/2, right? You can rewrite it as a limit of fx to power 1/2, right? You know that. And then I can make it become, using the problem 6, I can just make this like this, limits of fx when x go to 2 to power 1/2 here. And then you're gonna use a given limit of fx when x equal to 2 equal to 4. And 12.5, that's going to give me 2 as the answer. So that should be it for example number 9. Okay, let's move to the next page. So here we have direct substitution property, which is very important on, okay, important. So this property helps you to find the limits easily later. So if f is a polynomial or rational, ratio of polynomials, and c is in the domain of f, then limit of fx when x equal to c will be equal to fc. Okay, so function with this property are called continuous, right? So yeah, any function that's that can use property here is continuous one. And we will study this concept more. So let's try to evaluate the limits in example number 10 here. So remember that all these are what? A polynomial. Since it's polynomial, then it's continuous from net infinity to positive infinity, because there's no hole, there is no point that undefined, right? So I can right away apply the direct substitute property in here by substitute the x equal to 5 into the polynomial. So it's going to be 2 times with x now become 5, right? 5 squared minus 3 times with 5 plus 4. Here we go. And now use a calculator. You can have 50 for the first term minus 15 plus 4, and that's going to give you 39. Okay. So now take a look at the next one. Now I have limits of x cubed plus 2x squared minus 1 divided by 5 minus 3x. So what is this? This is a rational expression, right? Since it is a rational expression, you need to make sure the bottom not equal to 0, right? So so domain is 5 minus 3x not equal to 0. Okay, so then what does that mean? X cannot equal to 5 divided by 3, right? Okay, so that is a domain. So it can be anything, but not 5 cannot. It cannot be that number. So now what you do? According to the direct substitute property, if f is a polynomial or a ratio of polynomial, right? So this is a ratio. Also, this is a ratio. So note, this is a ratio of polynomial. This is a ratio of polynomials, right? And we have -2. X go to -2, right? We should know that. Let me have and -2 is in the domain, right? Is in the domain. Let me maybe write it down here. In the domain, right? Because -2 is not equal to 5 third, so it is in the domain. Okay, so now it's time to substitute, direct substitute. So I have x equal to -2, right? So I put -2 to power third plus 2 times with -2 to power 2. Make sure that all the x now change to be -2, right? If you guys forget this, forget to the way to substitute, Please focus on this, right? 5, the bottom going to be 5 minus 3 and multiplied by x, which now change to be -2, right? Wherever you see there's an x, change it to be -2. Now, use a calculator, you're going to have what? -2/3 going to be -8 plus 2 times -2 to the power 2 is 4. And minus 1 divided by 5 plus, because the negative and negative is plus. So 5 plus 6, because 3 times 2 equals 6. Okay, use a calculator, you will have answer as -1/11. I hope I'm not doing wrong, but this should be correct answer. All right. So, question, what happens if the limit is 0 for the denominator? What happens if the limit is 0 for the denominator? So, suppose I'm interested in the limit of a function at the point A. With key idea is if two functions are identical everywhere except at point A, then their limit match everywhere, even at point A. So mathematically, if fx equals to g of x, when x not equal to A, then limits fx when x equal to 2, sorry, x equal to A, going to be equal to limits of g of x when x equal to A. Is provide the limit exists. Okay. So we have some problem about this topic. Okay. So take a look at example 11 here. We have find the limits with x squared plus x minus 30 over x minus 5 when x go to 5. If you right away that substitute, you're gonna see, oh, it's gonna be 0 as the bottom, right? So so what you do is you should not do it right away. You shouldn't direct substitute right away. What you do is you need to factor. Okay, you need to factor all the top and bottom and see what happens. Okay, so note, if you use direct substitutes and make a 0 at bottom of at the denominator, then you should try to factor the rational first. Okay, so let's try to factor it. If you still remember the way to factor from math Pythagoras and math 115, you should know that x squared plus x minus 30 will be equal to the limits of x go to 5 first, right? The top now change to be two factor, which is x plus 6 and x minus 5. So remember that why I have this, I have using AC method, right? And you see that 6 times -5 will be equal to -30, and 6 plus -5 going to be equal to 1. So that's 35, right? And then divide by the bottom as x minus 5, right? So you see over here, we have a common factor between the top and bottom. So you should cancel it first, right? So now you will have the limits of only x plus 6 when x go to 5. And now you can direct substitute. So 5 plus 6, and without any issue, it's going to be even 11. Okay. Also note that x equal to 5 is not in the domain, right? In the domain, so you cannot use direct substitutes, right? Okay. So let's move to the example 12. I have limit of x squared minus 4 divided by x minus 2 for x approach to 2. So again, note that x equal to 2 is not, oops, what happened? In the domain, right? Because you see that the bottom is x minus 2, so domain should not include x equals 2. Okay, so now you cannot use, maybe I'm gonna say cannot use direct substitutes. Okay, so you have to do factor first. So I have limits for x equal to 2 of so top now you see it is a different of 2 square, right? So it's going to be x square minus 2 square over x minus 2, right? And I actually can rewrite it as limits of x go to for x equal to 2 of x minus 2 times x plus 2 over x minus 2. Okay, so now you can see that, oh, you actually have a common factor between top and bottom, and you can cancel the case that makes x x minus 2 x equal to 2 gonna be 0 at the bottom. So at this case we can have only x plus 2 after cancel x minus 2, right? Also after also you now can direct substitute because there's no more issue with the bottom, right? So you can be 2 plus 2 equal to 4. This is the answer. Okay. One more note that I think you should also think is usually you will have you should have, right, a common factor between top and bottom. Actually, I'm gonna leave that for you to know. So usually you should have a common factor between top and bottom, so you can cancel the bottom, and you can use a direct substitute later on. Other than that, you will get like undefined limit. Okay. Okay, let's have do example number 5. You can, I will let you guys try to do this problem. Make sure follow um, all the thing that I did show you. Firstly, try to substitute x for into the bottom if it's undefined. If it's not into the domain, then you cannot direct substitute, right? Then you have to think about factor top and bottom. Okay. So now exercise number 6, you will try. And now we're going to move to example 13. Okay. It says evaluate. Okay. We have limits of 3 plus h, and parentheses 3 plus h squared minus 9 divided by h. Okay, so for this case, you should try to do distribute the top. So you're gonna have what? 3 square. You apply the perfect square form, right? You have the perfect square form, 3 square plus 2 times 3 times h, oops, plus h squared, and then minus 9. So if you forgot this form, what you do is you can easily find it by just distribution 3 plus h times 3 plus h. You will get the same thing as this one. Okay. So now I forgot a limit put down here. So I put a limit here, right? Divided by h for h go to 0. Okay, I forgot to tell you that at first you think if I can direct substitute, but actually you know that with h equals 0, it's not in the domain because we have h at the bottom here, so you cannot using direct substitute, right? So you had to factor it. But before doing factor, for this case, I would love to distribution first. And try to combine like term and see what happens. So I have top going to be equal to, let me write limit first. Right. Top going to be equal to 9 plus 6h plus h squared and minus 9. And you see here, I saw that there is positive 9 and negative 9 that can cancel on the top. So I can rewrite it as 6h plus h squared divided by h. And then you have h, you can factor h out, right? Now you see that if you factor h out, you can cancel the bottom. So you have 6 plus h, get another factor. So you have h here. Oh, I forgot the limit. For h equal to 0. Okay, so now you will see that there is a common factor between h between the denominator and numerator. So now you have just 6 plus h, and you can direct substitute with equal to 6 plus 0, and that equals 6 as the answer. Okay. Okay. So now, what about we evaluate limits of square root 1 minus h and minus 1 divided by h. And remember that in this case, again, since we have h at the bottom, then domain is not include h equals 0, right? So so you cannot direct substitute. But what should you do in this case? Can you see, can you factor something? Sometimes it's not easy to factor, right? You see that? There's no common factor, no common factor between two term on the numerator, but I see there is square root here. So I would like to say, I in this case, which is like a special, and I would like to make sure everyone should remember this case. Okay, special with square root, right? If you see a square root in the denominator or numerator and minus or plus with something, you're gonna have to think about multiplying with the conjugate of this group. So think about this. Do you understand conjugate? Okay, maybe you guys forgot. Like a minus b, the conjugate of it will be a plus b. So this is conjugate of this is conjugate of this one. So it just conjugate each other. If you see like a plus b, you can have a conjugate of it is a minus b, or you have a minus b, then you have conjugate is a plus b. So in this case, I would like to multiply the top with the conjugate of s, which is square root of 1 minus h plus 1. Why I do this? Because I don't like, and you will not do, you cannot do anything if you just keep the square root, right? You need to make, you need to take it away. How can you do it? Only you multiply by the conjugate of it, so you can square, you apply the form, the difference between two square two positive square, right? So you can apply it and then eliminate the square root. Okay, so now since you multiply the top with that conjugate, then the bottom you have to multiply with the same thing, right? Okay, so now what you should do, you should have top as, okay, so remember the formula as a squared minus b squared going to be this, right? Now you're going to have top as square root of 1 minus h square, right? That is a, right? And you minus with 1 square, and you divide by h time with square root of 1 minus h of plus 1. Okay. So let's see what happened now. Look like I forgot the limit, right? Forgot the limits when h go to 0. Okay. So now what's next step? Top. Now I can cancel the square root and become 1 minus h only, and minus 1 over here, divided by h times with the square root of 1 minus h plus 1. So you can see that there is positive and negative number 1. And oops, why did you need that? Okay. And you still have a negative h here. So you can rewrite it as limits of h go to 0 for the top as negative 1 multiplied by h divided by h times square root of 1 minus h plus 1. And now you can see that there is common factor between top and bottom, which is h, and that is the one that I want to cancel because I need to take away the h at the bottom. So there is no issue with h equals 0 when I direct substitute in, right? So now I can just have negative 1 on the top, and the bottom will be square root of 1 minus 0 plus 1. All right. Now, simplifiers, I have, let's have negative 1 top, and bottom going to be square root of 1 plus 1, which is equal to 2. That's going to be the answer. All right. Okay, let's move to the next. All right, so I really like to let you guys to work on these two exercise, and we're gonna group work together, and we're gonna put together on these two exercise in class, right? Okay. And now, we're gonna recall the fact for the limits to exist, it means the limit from the left and from the right? So they must exist and they are equal each other. So limit fx when x go to a equal to L, that means what? Limit of fx equal to limit limit of x when x go to a from the left hand side over here, right? Equal to the limits of fx squared x go to a from the right hand side and equal to L. That it, right? you need to remember this from the this is a fact. Now, even though this say exercise to try number 9 here, but let me help you to do this one. Okay, using the diagram below, determine if either limit exists. Actually, I think some of you can handle this one. So you can pause my video and try it first. Then you can resume my video to see what I solved the problem, right? So for the limits when x a limit of absolute value of x when x go to 0, if you see from the graph over here, here is point x equals 0, right? To find the limits of x when x go to 0 from the left hand side, let's see what happened. The graph try to reach to this point. Okay, it's approach to this point. What is that value? Okay, let's see. Oh, the value is equal to 0. What about the right hand side? So I'm gonna say here's limits of absolute value of x when x go to 0 from the left will be equal to 0, right? And what about the limits of absolute value of x when x go to 0 from the right? Is also try to go to the same point here, and that gives us the value as 0. So they are equal each other and equal to 0. And then I'm gonna say the limits of absolute value of x when x goes to 0 will be equal to 0. Okay. Let's take a look at problem B here. When limits of absolute value of x over x when x go to 0. Let's see from the left hand side, limits of absolute value of x over x when x go to 0 from the left is try to go to where's 0, where's x equal 0? Here is x equal 0, right? And the graph try to go to this point. What is that value? I would say -1, right? So this one equal to -1. Okay. Now let's try for the right hand side. This is the limits of absolute value of x over x when x go to 0 from the right hand side. Okay, so you can see is try to go to this point, this value. What is that going to be? 1. So equal to 1. So you can see that they are not equal each other, right? And according to the previous section, you should know that this is do not exist, right? Okay, so let's move to the next page and see what happened. Okay, I have squeeze theorem. Squeeze theorem. In my notes, I also say it is theorem number 1, but you guys can remember it's called the name of it is squeeze theorem. All right. So if you see, if you have fx less than or equal to g of x and less than or equal to h of x, when x is near a and limit of fx when x go to a equal to the limit of x when x go to a, right? Then this one will be the limits of g of x when x go to a will be equal to L. Okay. So you can see the graph over here. Here the blue one is F. The red one is G and H1 is green. And you see that's when limit of fx equal to the limit of hx, it actually is at x equal to a at this point. So then that's gonna be equal to L, which also is the limit of g of x when x equal to a. Okay, so yep, that is the the theorem from the squeeze theorem. This also called Sandwich theorem, and it say that if g of x is squeezed between fx and hx near a, and if f and h have the same limit L at a, then G has to be forced to have the same limit L at A. Okay, so from two limits of two different two different function, you can squeeze and know the value of the limits of the like another function limit of another function. Okay, so let's try to apply this on this limit. So we want to show that limit of x squared times sine 1 over x equal to 0 when x go to 0. So we know that for sine of 1 over x, right? It is since it's like a sine function. You guys should remember that this is less greater than or equal to -1 and less than or equal to 1. Okay. That is our first thing. Second things, maybe I don't even need to have this one. Second thing that we also know, since x squared is to say is positive, right? Greater than or equal to 0. So you will have x squared multiplied by sine times 1 over x. We will not change the direction of the inequality, right? Make sure that you multiply all both inside of x squared and multiply sine 1 over x with x squared, right? You did multiply this with number 1, okay. All right. Now let me just try to have another color so you know that we just multiply with x squared for from this one, right? And because of x squared greater than 0, so then the inequalities do not affect at all. So now, okay, you will have you should know that the limits let me say limits of x squared. Oh, I say negative x squared in here because it's be negative. When x go to 0, what is that equal to? And you can direct substitute and make it equal 0, right? We know. Okay, so also, and what about this side? Limits of x squared when x go to 0. What happened? Direct substitute equals 0. So you see that this exactly the case of the squeeze theorem. So I'm gonna say apply squeeze theorem. We have the middle inequality, the middle of the inequality, middle expression will be, so I'm gonna say I have limit of the x squared times sine 1 over x here, for x go to 0 will also have to be equal 0. So that should be it. Okay. Take a look at the graph over here. You can see that the graph, the red one should be, let me see. The red one should be limit of x squared times sine of 1 over x, okay? And the green one is y equal to x squared, and the blue one is y minus x squared, right? See that? They are all intersect at 0, 0 here, okay? So, okay. Let's try exercise. Oh, actually, I'm gonna ask you to do to try problem number 10 over here. Remember that we're gonna try to use a squeeze theorem on this. Okay. Okay, so we're gonna stop this section 2.4, and I will see you next time. So